right. Yeah, so thanks very much, and thanks to the organizers for making this possible on very short notice. Yes, so I'm going to talk about the post-Newtonian expansion and specifically about work done together with Johannes Blümlein, Peter Marquardt, and Gerhard Schäfer. And well, since I'm talking to experts, I'd like to go directly to the post-Newtonian expansion. That is, we're looking at a binary system, which I've sketched up here. Two compact objects at large distance r and small radii, say rs, which emit gravitational waves with wavelength lambda. And just to make the argument slightly simpler so that we don't have to do any maths in our heads, we can assume that the masses are comparable, but the whole argument also goes through if they're not. And we're interested in the case where the system is non-relativistic, so small velocities. Initially, those compact objects are far away from each other, and the system is essentially Newtonian. And then the virial theorem tells us that the kinetic energy is of the same order as the gravitational potential energy, which naturally gives us a relation between the velocity and the coupling. And since we said the velocity is small, this gives us this expansion parameter, which defines the post-Newtonian expansion. And also this is a scaling parameter, which relates the different scales we have in our problem. So looking at the frequency of these emitted gravitational waves, those are of course given by twice the orbital frequency, since those are quadrupole waves, which is of the order of the velocity divided by this radius. Or in other words, the wavelength here is of the order of this distance divided by the velocity, by the small velocity, so the wavelength is large. And on the other end of the spectrum, we have the radii of these small objects, and assuming those are black holes, that would give us the Schwarzschild radius, and using then the relation between coupling and velocity, this tells us that those are of the order of the distance times velocity squared. All right, and we want to consider the system in an expansion and this small velocity, and there are different approaches how we can go about this. And I should add at this point that I'm only going to discuss conservative dynamics, so no energy loss through radiation. And of course, this post-Newtonian expansion has been considered essentially since general relativity has been conceived almost. And I'm not going to list the long history of traditional approaches, but those approaches culminated in a description at the fourth post-Newtonian order a number of years ago, and those were actually the first approaches which managed to arrive at that. Much more recently, so that's the latest approach, that's the Tutti Frutti approach, which combines different bits and pieces, and this has allowed to arrive at first results at fifth and sixth order. But I'm not going to talk about these approaches. I'm going to talk about the effective field theory approach, pioneered by Goldberger and Rothstein, where we also have complete fourth order description by now. And but in this talk, I'm going to go even further and talk about the fifth and the sixth order. And I'm going to explain why we still have a partial here in brackets and not really a complete result. But yeah, I want to outline the effective field theory approach. And the basic idea behind this is that that general relativity is complicated. So you want to have a simpler theory, which is, at least for the description of this binary system in the post-Newtonian expansion, at least in this limit, it should be equivalent. And quite generally, I mean, this is not, effective field theories have been considered also for quite a long time. And quite generally, the idea is as follows. You start from a full theory. And in this case, the full theory is, of course, general relativity. And in this full theory, you identify the relevant scales of your problem, and then expand the full theory action in small parameter which relates these different scales. And this we've already considered on the previous slides. That's in this case the small velocity, or equivalently the gravitational coupling. So let's have a look at this very concretely. As Radu already mentioned in his talk, we are looking at the general relativity action as a sum of the Einstein-Hilbert action, gauge fixing term, where we take a harmonic gauge shown here, and a matter term. And I'm going to simplify things a bit and assume that the matter is point-like. So I'm not going to look at tidal effects, which just start to become relevant in principle, they start to become relevant at the orders we are looking at, fifth and sixth PN order, but I'm going to neglect them for the time being. And I'm not going to discuss spin corrections either. So, and that makes this matter interaction, this matter part of the action very simple. It's just the sum of the two weld lines. As I said, this is the full theory action, and we want to perform a post-Newtonian expansion of this action. And this goes as follows. So we first expand in the small velocity. And looking at this weld line action, we can introduce a parametric time here, which gives us this square root of the metric, or of two four velocities contracted with the metric. And well, the four velocity means that the spatial components here are suppressed, and only at leading order in this post-Newtonian expansion, we only have the 0,0 component of the metric. So the message here is that the different components of the metric, the couplings of different components of the metric to our matter scale differently. And for this reason, we want to use a parameterization of the metric which takes this into account. And very convenient and useful parameterization was suggested by Cole and Smolkin. We take our metric and introduce three new fields. So we have a scalar field phi, a spatial vector A, and a spatial tensor sigma. And now reminding ourselves, so in the limit that these fields go to 0, we get back a flat spacetime, flat metric. So these fields parameterize the deviation from a flat spacetime, which is related, of course, to the coupling. Or in other words, this post-Newtonian expansion in small coupling and velocity implies an expansion in these fields. And once we perform this expansion, we get at an action of this kind. So we have these three gravitational fields, phi, the vector A, and the tensor sigma. And I want to emphasize that the sources here also, contrarily to Radu's talk, the sources are completely classical. And so the first line here shows the kinetic energy for the sources, just as one would expect from classical mechanics. The second line here is the interaction between the sources and these gravitational fields, and as one would also expect, they're proportional to the mass. And we have linear interactions. The interactions with the scalar are unsuppressed. The interactions with the vector are suppressed by 1 power of the velocity. The interactions with the tensor by 2 powers of the velocity. And of course, we also have interactions with higher multiplicities at higher orders. And then we have a purely, in the third line here, a purely gravitational part. So here are the kinetic terms for the gravitational fields, and here this ellipsis indicates then interactions between these fields. And once we've performed this post-Newtonian expansion of the general relativity action, this is a perfectly fine. This is perfectly well-defined. We can consider this as a perfectly well-defined quantum field theory, and we can take this action and derive Feynman rules from it. For instance, here. Interactions of matter with a scalar, spatial vector, or tensor, and so on and so forth. And of course, the idea is then that we use this or exploit this to use everything we know from particle physics at some point. But before we get there, we have to go through a few more steps in the construction of the effective field theory. So the first step was to identify the scales and to do this post-Newtonian expansion of the action. The second step is then that we identify field modes, which are characterized by the momentum scalings, and decompose our fields into these modes. And this was originally done in the context of non-relativistic QCD by Benecke and Smirnov, and they identified 4 relevant modes, namely potential modes, ultrasoft modes, which in the context of gravity are often called radiation modes, and then hard and soft modes. And I'm a little bit concerned that there is a bit confusion about that. There might arise some confusion about terminology. Some people group a number of these modes under soft modes. My understanding is that this then encompasses the potential, the radiation, and the soft modes themselves, but I'm going to stick with the original terminology. So here we are only interested in the classical limit, and it's quite straightforward to see that in this case only potential and radiation modes contribute. So these are these are characterized by the momentum scaling I've listed here. So the energy component is of the order of the small velocity over the separation. And for the potential modes, the momentum component is of the order of 1 over the radiation, or in other words, the wavelength is of the order of the distance. Whereas for the radiation modes, the wavelength is much larger. So the spatial momentum component is oppressed by 1 power of the velocity. And we then write our fields as a sum of these 2 modes. And whenever they appear together, we have fields with different wavelengths, which means that we should perform a multipole expansion. Now, when I mention multipole expansion, you might be tempted to think of well, multipole moments, monopole moment, dipole moment, and so on and so forth. This is not yet relevant. These appear at a later stage. I will come to that later on. At this point, the multipole expansion means what I've written down here, that you expand the fields in the radiation fields in a small position, so around x equals spatial x equals 0. So that's the second step, and that gives us, in a sense, the final form for our general relativity action. And now it's time to actually do the transition to the effective field theory. So we write down an ansatz for the action. So this effective field theory is known under the somewhat paradoxical name of non-relativistic general relativity. And the action has the following form. So we have a part which describes the matter. We have a part which describes interactions of matter to radiation modes, and a part which is purely consists of the radiation modes and has no matter inside. And the point here is that we got rid of the potential modes. So all fields we have in this effective theory are radiation mode fields. And to reproduce the effects of the potential modes had in the full theory, we have to introduce parameters. And in the matter action, which I want to focus on first, this is given by this potential. And this potential as you would expect, this potential at leading order in the post-Newtonian expansion will just give the familiar Newtonian potential, gravitational potential. I'm going to call this near zone potential to be more definite, because later on we will get we will consider additional contributions. And I want to distinguish these two. And well, apart from the near zone potential, we have the total mass and the kinetic energy, which are, of course, as in general relativity. And well, we introduced this as a parameter to absorb the effects of the potential modes. And this brings us to the fourth and final step. We want to determine this parameter by requiring that the two theories are equivalent up to higher orders in the post-Newtonian expansion. This is called matching. And one way to formulate this equivalence is to look at the path integral. And for the potential, we want to look at the case where we don't have any contribution from radiation modes. And you get, if you compare the two path integrals of the theory, so you get the following formula for the near zone potential. So it's the logarithm of this path integral over with the general relativity action minus the parts which are the same in both theories. And we only have potential mode contributions here. And as I said, this is a perfectly fine this perfectly fine as a quantum field theory, so we can do a perturbative expansion, which is part of the post-Newtonian expansion, and write down diagrams like here. So at zeroth order, we just have the exchange of a single scalar graviton now. Then at higher orders, we get exchanges of vector gravitons, or these diagrams which look like one-loop diagrams. And at higher orders, we also have tensor exchanges and more, in quotation mark, loops, because I'm saying calling these loops is not maybe not entirely correct, because since the classical the matter is classical, these solid lines here actually do not come with any propagators. So drawing diagrams like this in this context might be slightly misleading. So instead of drawing solid lines here, you could equally well draw these source dots here. And then you immediately see that this diagram here actually factorizes and is given by the square of this leading order diagram, this Newtonian diagram. So you have the logarithm of 1 plus this diagram, let's call it x, plus x squared over 2. And when you actually evaluate that logarithm, this diagram drops out, this factorizing diagram. And this actually holds true for all diagrams which factorize in that way. So what happens here is very much like what we know from quantum electrodynamics, for instance. So we have this simplified expression now for the near zone potential, and the only thing that's left to do is to evaluate the diagrams here. And for this, we can use well-established technology from particle physics. So to give a bit more technical overview, we generate the diagrams we want with a program called QGraph. We need to evaluate the diagrams with up to 5 loops. We get a number of diagrams which we're not really interested in. And we also want to take the classical limit at this point. And this is also pretty simple, thanks to the fact that our sources are already classical objects. So the only thing we have to do in that respect is to discard diagrams with graviton loops. And I've drawn here a selection of diagrams which we have in the end. So those are 5-loop diagrams. We also have quite a few more of them, and also diagrams with lower loop number but higher powers of the velocity. So and then we have to evaluate these diagrams, and for this we have to compute our Feynman rules and insert them. I've only shown one of the. I'm only showing one of the Feynman rules here to just give you an idea of how they look like. So it's a bit cumbersome, but if you don't try to do it by hand, this works reasonably well. And after you insert the Feynman rules and all the dust settles, which takes a while, you arrive at these propagator type diagrams, where all these lines are actually massless. And you get these diagrams essentially from the original ones by shrinking all matter lines here to points. And massless propagator type diagrams are very familiar object. So they're probably the most studied and also the simplest types of Feynman diagrams you can have. We can reduce these to a small set of master integrals using well-established technology, the Porter's algorithm, integration by parts. For the contribution with vanishing velocity, so v to 0 contribution, we just get 4 master integrals, which I'm showing here. If you also take into account velocity corrections, you get more master integrals with lower loop number. And what's very nice is that these master integrals are actually very simple. At least the first 3 ones. You can calculate them by hand. The last one is the only one which is a little bit trickier. But fortunately, this is also known. This was already calculated before it first appeared in the calculation of the potential. So, and yeah, it also has a pretty simple expression here. So you plug in the results for the master integrals into the reduction you have, and you get an expression for your near-zone potential. What I'm showing here is, for the time being, just the result for, or the contribution for vanishing velocity, because it fits very neatly in one line. It's a very simple expression. You see, it's essentially just a polynomial with rational coefficients. And this has been known now for maybe a bit over 2 years. What's new is that we now also have the velocity corrections here. and also parts of the potential at the sixth post-Newtonian order. And I'm going to give explicit expressions later on. At this point, one of the problems is that the expressions are quite bulky. You don't really see very much. But what I want to discuss already now is the structure of the result first, and then also the cross-checks we have. So, and this is what I'm showing here. So here I've listed the different contributing powers of the velocity up to v to the 12th order, and the powers of of Newton's constant. And here in the lower left corner, that's just the Newtonian potential, so 0 pn. Then if we add an order in the coupling, or 2 orders of the velocity, we get a 1 pn order, 2 pn, 3 pn, 4 pn, and those are of course very well known. What's new are these 5 pn and 6 pn lines we're interested in. And I've put, or let me first discuss these other bands here, which indicate the post-Minkowskian expansion, that is the perturbative expansion in Newton's constant. And there, as we just heard, we have now results up to the 4th post-Minkowskian order. So everything up to here is known from that side. And I've put check marks here for the calculations. So 1 check mark means we have 1 result, and 2 check marks mean that there are at least 2 independent calculations. And since everything up to 4 pm is now known, we always have 2 check marks down here. We also have 2 check marks up here for G to 6, V to 0. That's the static potential, which I just said was calculated in 2019 by 2 independent groups. Here, for the 5 pn potential, there's then only 1 structure which has not been double-checked completely. So we have 1 complete calculation and 1 partial calculation by these people. So this is now the near zone potential, but that's not yet the final answer. As was also discussed in the last discussion, this is not a physical quantity. It's gauge dependent, and starting at 4th order, we have infrared divergences. There's nothing to worry here, because whenever we calculate observables, we have to combine this with the contribution from the remaining radiation modes. But in the end, what we are interested in are not really radiation modes. We really just care about, say, more global observables. So one way to make this this cancellation of divergences manifest is to go to yet another effective theory. So what we want to construct is a completely classical action, which does not contain any field. I've never seen any name for this given to this theory, so I'm open for suggestions. For the time being, I'll just call it a classical post-Newtonian action. which is given by the integral over a completely classical Lagrangian, which has the form of, well, the total mass of the binary system plus kinetic terms minus a potential. And this potential now consists of the near zone potential, which I just explained in some detail, which we got from integrating out potential modes, plus some tail contribution, or far zone potential, if you will. And well, to get here, of course, our next task is to determine this tail contribution. Again, we use matching to the previous theory, that is matching, in this case, matching to NRGR, and which tells us that the far zone potential is given by the logarithm of this path integral now, where here in the exponent we have two components of the NRGR action. The first one is, so the second one is maybe less interesting. That's the pure radiation part, whereas the first here describes the matter radiation interactions. And to linear order in metric fluctuations, this has the form of a coupling of an effective energy momentum tensor to, well, the deviation from the flat metric, which we want to parameterize again in terms of our scalar, vector, and tensor field. As I said initially, these fields and this combination are multipole expanded. And once you apply integration by parts and use energy momentum conservation, you can rewrite this in terms, so now this energy momentum, so derivatives of the energy momentum tensor of energy momentum tensor components, you can then rewrite in terms of multipole moments. The leading moment, the monopole moment, is just the total energy of the system. And higher moments, for higher moments, we again distinguish between odd and even parity. We use the same names as in electrodynamics for this. Namely, we call these electric and magnetic moments. So the electric dipole moment is the total momentum. And once we go to the center of mass frame, this doesn't contribute anymore. And then the magnetic dipole moment is related to the angular momentum. And then we have the electric quadrupole moment. And of course, this is where, for the first time, something interesting happens. So we plug in this action, and again, we can perform a diagrammatic expansion of this expression, which gives us the following formula for the tail contribution. We are only interested in the conservative part here, and that first arises at the fourth order and is given by the sum of these six diagrams over here, where we have the couplings of radiation gravitons. So only radiation modes are left, and those couple to the multipole moments. In this case, it's one coupling to the energy and two couplings to the electric quadrupole. So this is the fourth order. At fifth order, the idea is that you get contributions from further multiple moments, namely the magnetic quadrupole and the electric octupole, which gives you, and you get a number of additional diagrams, but all these diagrams are two-loop diagrams, so they have the same structure as these. You also have to consider potential contributions to the multiple moments themselves. So you have these diagrams here, but with 1 pn corrections to the multiple moments. And since we're working in dimensional regularization everywhere, we have to be careful and use d-dimensional expressions for these multiple moments, which are fortunately none. And yeah, so this was calculated initially in 2019 by Ricardo and Stefano, but there have been a number of revisions. So the latest form of these results is from this year. And we've checked at least earlier revisions and done comparison there. So then we take this far zone potential tail contribution and combine it with the near zone potential, which gives us this classical Lagrangian. What's a bit inconvenient about this is that at this point, the Lagrangian depends not only on the positions and the velocities, but also on accelerations and higher time derivatives. You might even get a bit worried about Ostrogradsky instabilities, but this turns out to be not a problem. You can actually eliminate these higher time derivatives using total derivatives. So adding total derivatives to the Lagrangian, adding terms to the Lagrangian whose variation vanishes at the current post-Newtonian order. So these zeros, Z1 and Z2, are solutions to lower order equations of motion. And the last tool you can, so if you only use these two here, you can get rid of everything except for one acceleration in each term, at most one acceleration in each term. To get rid of the remaining acceleration, you have to leave harmonic coordinates. And this you can do with these coordinate shifts. As is often the case when constructing effective theories, we don't retain the full symmetry of general relativity. So we don't. Yes.
Means 15 minutes, including the discussion.
Oh yeah, thanks. I'm going to finish very soon. Yeah. So what I wanted to say is that we don't have the full diffeomorphism invariance of general relativity anymore, but we have a residual symmetry. So we are allowed to shift positions by a small amount, in the sense of the post-Newtonian expansion. And once we have a Lagrangian which only depends on positions and velocities, it's completely straightforward to go to a Hamiltonian. And the advantage is that this makes it again trivial to go to a center of mass frame and simplifies expressions. And we also do this in order to being able to compare with other people's results by applying canonical transformations. to the Hamiltonian. And I'm now going to show the expression for the Hamiltonian, just to give you an idea about the structure. So we introduce the reduced mass here, rescaled momentum in the center of mass frame, rescaled distance. So we rescale it with the total mass and the gravitational coupling. And we also have a radial unit vector appearing here. And then we get an expression of this form here. So it's very simple. Again, it's mostly a polynomial. We have different powers of the reduced mass here. So this is linear power in the reduced mass squared, and on the next slides we've also seen cube and the reduced mass to the fourth power to the fifth power. And these two first, so the linear and quadratic power in the reduced mass, they come with logarithms, and these factors pi squared. So as you can see here, and here we have the quadratic power, the logarithm, and on the next slide, the pi squared. Once we get to the cubic order, there are no logarithms, no pi squares anymore. And here, fourth order, fifth order. And the reason for this is that the source of these logarithms or these logarithms actually arise from an interplay between the near zone potential and the tail. And the tail only contributes to mu to 1 and mu squared. So that's the reason why we only have the simpler structures for the other powers here. And I'm not listing the full tail contribution here, the full far zone potential. I'm omitting the finite non-logarithmic part. Because, as I will comment on in a minute, we are not very confident in this part, but the rest is fine. And of course, once we have a Hamiltonian, we can use this to compute observables like the energy or the peristron advance. And before concluding, I want to briefly mention the checks of this. So the zeroth power of the reduced mass corresponds to the Schwarzschild limit, and this is of course very well known. For the first and second power, we know we've seen that we know that the far zone potential and the near zone potential are separately divergent, and we see that these poles cancel in the combination between the two, as they should. For the higher powers, starting from cubic powers, we can compare with the results from the tutti frutti approach and find a full agreement. They have also results for the linear power, but here we find that we find that we can get agreement if we apply this kind of finite renormalization to the magnetic quadrupole moment. And for the square power here, I'm not aware of any results we could compare to. All right, let me briefly summarize. We can use methods from particle physics, especially effective field theories and multi-loop calculational techniques to tackle the problem of post-Newtonian expansions. The current state is that we have the complete 5pn near zone potential and parts of the 6th order contribution to the potential. But there seem to be issues when combining this near zone potential with the tape. So thank you very much.
Thank you very much for the nice talk. So I am looking for hand raising. I have one by Thibaut. Thibaut.
Let me unmute. Okay. Thank you, Andreas. I wanted to ask about your magnetic quadrupole.
Yes.
Did you compute it in d dimensions? Because you say you use it. I mean, it has a 1/epsilon pole, so it has no meaning to compare anything except if you compute it in d dimension and in a good sense.
What
did you compute?
So of course the magnetic quadrupole moment itself doesn't have a 1/epsilon pole. The 1/epsilon pole comes from these diagrams which involve the magnetic quadrupole, and that's why we need the finite 4-dimensional part of the magnetic quadrupole plus order epsilon contributions to that. And this is quite a bit here. Depends on how you define how exactly you define your quadrupole moments or your multipole moments in d dimensions. You have some freedom there.
This should be defined from the full irreducible decomposition of vector and tensors in d dimensions.
Absolutely, and this is also the result that we used. What I mean is, after doing this decomposition, you can in principle, if you want, you have some freedom in introducing overall factors. So overall constant factors, which of course in the limit d going to 4 have to go to 1. So and that was actually our motivation at even considering this kind of finite renormalization.
Yes, but what is the Jij on the right that you multiply? It's the 3-dimensional one. Without
no, it's a d-dimensional one. It's essentially okay. So in the 3-dimensional one, you a priori have epsilon tensors, Levi-Civita tensors, and then you have to first state how you define those. So what does this even mean in d dimensions? And depending on what you choose there, you get different expressions. So I can look up the explicit expression we used, but I don't have it ready off the top of my head.
Okay.
Sorry, Andreas, but what he was asking is that this Gij should be finite, and therefore the epsilon doesn't matter. So how do you get a pole on the right-hand side?
This Jij is finite.
Then the epsilon y shouldn't matter, right?
Yes, it does, because the coefficient of this Jij, which contributes here to the Hamiltonian, that coefficient is divergent.
So you input it already in the answer here on the pole. I see.
Yeah. So here in these diagrams, so you get some expression which is proportional to the energy times square of the magnetic quadrupole moment, or depending on how you distribute derivatives.
You take that Jij to
derivatives,
the
and
exact,
then you have this diagram as a coefficient.
That's right, and that renormalization is on the exact three-dimensional Jij.
What do you mean with
The
renormalization?
Jij that you have there that says if you shift it to 1 minus 3 epsilon at the end, right? That Jij is the d equal 3 Jij.
No, it's not. It's not the J. This is not the d equals 3 Jij. So
But
we
the difference would be epsilon.
sorry,
Sorry, but you have single poles only, or you have quadratic poles as well now.
No, we have single poles.
And then the difference will be epsilon squared. No? Anyway,
why is that?
Because
So you have a finite. Here on the left hand side you have a finite contribution and an order epsilon contribution.
no, I understand, but the piece one third epsilon Jij is multiplying when you add this piece the d equal 3. That's the difference, right?
Yes. That's the difference. Yes. Sorry, I misunderstood your question.
Yeah,
yes.
That's what I was saying.
Yes, the difference is this multiplied with the finite part, multiplied with the pole in the coefficient.
Yes. So you're not So you're not confident on the answer because of these issues. Because at 4 p.m. we had the same problem, and we also did the d dimensions, and we also had to do the quadrupole to order epsilon to get the correct answer.
Yes, you do have to do the quadrupole to order epsilon to get the correct answer. This is not the question. It's just that the original expression we have for the magnetic quadrupole here, this is already in d dimensions. This should, in principle, include the order epsilon terms. But we have to somehow adjust the order epsilon terms to get agreement with Thibault and friends.
I see. But then you are not confident because of this disagreement. That's your lack of confidence.
Yes. So there could be many different reasons for this. But we are very confident that the near zone potential is correct. Let's put it like that.
I understand.
Okay, we shall take another question. Thibault, you still have your hand raised, but probably this is for your previous question.
Yes, it's although at the new square level, there is the issue that in your paper, Andreas, you say that you have discrepancies with Fofa and Storani 5PN NLO contributions. So do you want to comment on that? I mean, they computed some numbers, and then do you disagree with the rational numbers they get?
As you may or may not have noticed, since we wrote our paper, the original version of our paper, so we were of course discussing with them, and they decided at some point that Feynman propagators are not the correct way to calculate the memory term, and that changed their mu squared result again. So we're still discussing this. Let's put it like this.
But do you agree with their statement, in principle, about the use of propagators?
I don't have a final opinion on this.
Okay, thank you very much